back on track and all that. What's going on? Oh, okay, that is going. All right. So here we're going to be starting chapter 8. Is that right? That's the number, the next number. Yeah. So here in chapter 8, we're going to talk about exponential and logarithmic functions. The first half of this chapter we'll spend talking about exponential functions. And after that, we'll spend the second half of the chapter talking about logarithmic functions. And at the end of the chapter, we'll kind of tie those two functions back together because they are quite related, and we'll go back and do some exponential stuff after we have the logarithmic tools that allow us to do some problems that we saw in the first half of the chapter in a little bit easier fashion. But that's kind of how this chapter is going to play out from an organizational standpoint. So today we're going to start talking about exponential functions. And specifically today we're just going to do a little bit of definition for exponential functions, a little bit of vocab, and talk about graphing. And that's really the whole plan for today. So it's not a tremendously long or involved lesson. It should be relatively straightforward, so it shouldn't be too bad. So let's start with a little definition here. So we say that an exponential function can be written in the form y equals a times b to the x minus h plus k, where a is non-zero, b is greater than 0, so it has to be positive, and b cannot also equal 1. So let's think for a minute about these three extra requirements here at the end of why they're there. So why are we requiring that a has to be non-zero? What would happen if a was 0? Justin? Good. So if a is 0, 0 times b is just going to be 0, so you're left with just k then, right? And y equals k is just like a constant, like a linear function, like a straight line. That's not what we want to talk about. So you're absolutely correct. That's why we're requiring a to be non-zero. Why are we requiring b to be positive? Why does b need to be positive here? It's a little bit trickier to see. So a negative inside of an exponential isn't necessarily a problem, but it could be for some kinds of exponentials. What kind of an exponent would be a problem if there was a negative number in the base there? We saw this just last chapter. So if I have a exponent that's a fraction that has an even denominator, like if the exponent was 1/2, we know that's the same as a square root, and that's a problem if we're having the square root of a negative number, right? So that's why b has to be positive, because x is in the exponent. The exponent could be something like 1/2, which would give us problems if we tried to do negative number to the 1/2. Everybody's okay with that idea? Okay. And the last requirement is that that value for b cannot be 1. Why do we have that requirement? Harley? Oh, we can take the square root of 1. The square root of 1 is just 1, though. And in fact, what is 1 to any power going to be? 1. So really what that would turn into then is just a plus k, right? Which is a constant function again, and not what we want to be dealing with. It just would be just a straight line, which not what we're interested in. Does everybody feel okay as to what those, or why we have those 3 requirements there? Okay, good. So there are 2 types of exponential functions. There are exponential growth functions and exponential decay functions. So when we say growth, what do we suppose is happening? Things are getting bigger, right? If we're looking at the graph, what would we expect the graph to look like as we go from left to right? It'd be going up. Everybody's okay with that idea? And decay then would be things getting smaller, so as we go from left to right, we'd expect it to be going down. Everybody's okay with that idea? So if I look at my equation for my exponential function, which one of the parameters, a, b, h, or k, do you suppose is going to be the indicator to whether this is going to be growing or shrinking? It's the b, yeah. So it's the b that's going to tell us whether we have a growth or decay function. So an exponential is really just multiplication over and over and over again, right? Like 2 to the third is just 2 times 2 times 2. Everybody's okay with that? So in the case of exponential growth, something like if the b value is 2 would be exponential growth, because if I multiply that 2 over and over and over again, it's going to keep getting bigger and bigger and bigger, the result, right? So in general, what kind of numbers for b are going to give us exponential growth? So what? Well, like, can we be a little bit more specific? Because not all fractions are going to work. What? So those are all examples of ones that would work: 3/2, 4/2, 5/2. But there's a key distinction here that we're kind of still circling around. You're right, all of those are going to give us growth, for sure. But there's still a cutoff here that we haven't identified necessarily. Maddie? So positive is true that b, but we know b has to be positive anyways. But there are some positive numbers that are going to give us decays still. So we have to be a little bit careful there still. So think about a number that I can multiply by itself and get a bigger result. So like 2 times 2 gives us 4. That was bigger than 2, right? So squares, again, those work, but they're not like the minimum cutoff. What number, when we multiply it to itself, doesn't change? 1. So we want the numbers that are more than 1 or less than 1. More, right? So as long as that value for b is bigger than 1, when I multiply that number by itself over and over and over again, it keeps getting bigger and bigger and bigger and bigger, right? So the decay happens when the number is less than 1, but specifically we should say between 0 and 1, since we know that the b value can't be 0 also, or can't be less than 0. So the decays happen when you also have fractions, but they're fractions that are less than 1. They're proper fractions. Things like 1/2 or 2/3 or 5/6 or whatever. Everybody's okay with that idea? And exponential functions are often, or are actually quite important. These are things that we can use exponential functions to describe things that we interact with, in a lot of different disciplines. How many of you guys are in a chemistry class right now? You guys talked about like radioactivity yet?
No.
Or radioactive decay?
No.
Half-life, exactly, yes. So some of us have talked about this then and there. You just know what that is? Okay. Well, that's an example of a behavior that can be described with an exponential function. So if you're not familiar with this, if you have an element that's radioactive, what happens is it loses part of its atomic structure, some parts of its nucleus or electrons or whatever, and turns into another element. That process is called radioactive decay. And one of the ways that we measure how radioactive a substance is by its half-life. It's the amount of time it takes for the mass of that element to be reduced in half because it's losing part of itself through this radioactive decay process. That process happens exponentially. Growth, examples of growth. How many of us are in a biology class or have taken one recently? Okay. You guys, so what's a thing in biology that might grow exponentially? Anybody with a guess here? So populations tend to grow exponentially. So if you are like culturing a bacteria, the amount of bacterial cells in your culture would grow exponentially, at least up into a point where you've run out of resources or whatever. Like if it fills up your plate that you're doing your bacterial culture on. Or in the case of like an organism, like in the real world, again, populations tend to grow exponentially unless there's some like limiting factor introduced, like a predator or like, habitat destruction or something like this. How about any of us in an econ class right now, an economics course? Okay, several of us. There's another quantity related to money and finance that tends to grow exponentially. Does anybody have an idea there? Thinking about what we know about money or finances? Well, not quite the stock market, but related to that. So it's it's we'd say like interest, like compound interest grows exponentially, so your savings accounts, or if you have an investment that's guaranteed some amount of growth per year. So if you had invested in, say, the stock market, and you just bought like an index fund that is like, you're buying just like, you know, an even weighted amount of each of the stocks from the Dow Jones 500, and you just sit on that for like 30 years, your investment's going to grow exponentially because the stock market over time has shown that it's going to be increasing, and the value of that investment would grow exponentially. So the stock market itself, maybe not exponential growth there, but an investment in, you know, a stock market fund could grow exponentially. At least in terms of how it's structured. There's a lot of different ways to structure those sort of things financially. So, but that's really beyond the scope of this class. But the idea here is I just want to connect what we're doing to some things in some other subjects to show you that at least this class of functions in particular is a very useful one in a lot of other disciplines that we'll look at, especially in this chapter, kind of a lot of relatively simple story problems that tie into some of these other subjects outside of just strictly a mathematics problem where we'll give you an equation and ask you to solve for x. Because we can write some simple problems that are within the realm of our skill level in terms of the mathematics involved that involve these other subject areas, which is nice to get, you know, escape the realm of just numbers and tie in some, you know, application here. Okay. So let's just do a couple of examples to see if make sure that we're okay with determining whether an exponential function is growth or decay. So I'll just write down a couple of exponential functions and we'll decide whether it's growth or decay and make sure we explain why so everybody's on the same page. So if we look at y equals 3 times 5 to the x plus 1 minus 6, is this growth or decay? Growth. Great. How do we know that? Yeah, the b value is 5, which is clearly greater than 1.
So really the only way it could be decay is if it's like a fraction or a decimal?
Well, it has to be less than 1. So not all fractions, right? Like if you had 3 over 2, that's still growth, right? But the possibility of being decay would have to be either a fraction or decimal, although not all fractions or decimals are going to be decays. But yes. So for example here, this one is still growth, even though the b value is a fraction, because that fraction, 3 over 2, is still bigger than 1. However, if I look at this one, this is decay, because the b value here is a half, which is less than 1. Do we feel okay about picking out growth and decays? Pretty simple to do that. All we have to do is identify the b value and look at if it's bigger or smaller than 1. It's not too tough. Let's now talk about graphing. So to graph an exponential function, we're going to do three things. So the first thing we'll do is make ourselves a 5-point XY table. And we'll pick our x's the following way. We'll do -2 plus h, -1 plus h, 1 plus h, and 2 plus h. That's how we'll choose our x values. And then to find our y values, what can we do? We can just plug the x's into our function, or I can give you just like the way to find them. Either approach is fine. So again, that's how we can find the y coordinates, or you could just plug the x into your function. You'll get the same result either way, so it doesn't really matter. So do whatever you're comfortable with. The disadvantage here is it's like another thing to memorize when really all you're doing is plugging stuff in into the function. But if you want to just, if you're better with that than this, or you like the other way, do whatever works for you. I'm not picky about that. So for the graph of an exponential function, it has a special feature called a horizontal asymptote. When we say the word horizontal, what do we mean? Yeah, it's like moving left and right? Like flat. Are we familiar with this word asymptote? Is this something that we've talked about before? You've heard in another class? Okay, well, let's define that really quick. So an asymptote is like a line that the function approaches but does not cross or touch. So like one end of our graph is going to be moving very close right next to the asymptote, and the other end would probably be moving away from it, or maybe looping back down and then moving right along next to it again also, depending on the kind of function you're dealing with. But it's just an imaginary line. In this case, since it's a horizontal line that's like a barrier that our graph just isn't going to cross that line. Everybody okay with that idea? So when I talk about the horizontal asymptote, most of the time I'm going to abbreviate that just as HA, because that's a lot of letters and kind of a mouthful. So I'll probably just write HA as an abbreviation there. And for an exponential function, we can find that horizontal asymptote with the equation y equals k. So those are the two things that I need in order to graph my exponential function. So I need to know how I'm going to pick my x's and y's and be able to find that horizontal asymptote. If I have that information, I will be able to draw a good graph. Worth noting that it is kind of important that we are choosing our x coordinates in this fashion, because exponential functions, depending on whether it's growth or decay, can get very, very big or very, very small rather quickly. And if you're not careful about how you're choosing your x's, you might be trying to graph the point 1, 2, along with the point like 5 and 10,352 or something, which is not really very feasible for us. Although you might have the correct points, like putting those on the same sheet of paper is not really practical. So by choosing our x coordinates in this way, we're going to make sure that we don't end up with something that's just kind of silly trying to graph on our sheet of paper. Okay? So it has nothing to do with like the values you're getting. You could pick any value for x and it's going to be fine. But you just don't want to get like values that are inconvenient to deal with. You know what I mean? So let's do a couple of examples here. So let's say we want to graph y equals 3 times 2 to the x plus 1 minus 4. First thing I'm going to do is I'm going to identify the values for a, b, h, and k, because I'm going to use those values when I make my xy table. So what's my value for a? 3. And my value for b? 2. And my value for h? Be careful. -1. Remember, the h is always the opposite sign of what it appears in the function. And the k is -4. Okay? So now we'll make our xy table. So I'm going to have -2 plus h. And notice that I just wrote as a subtraction symbol since I'd be adding a negative. And then -1 plus h, 1 minus, or I'm sorry, 2 plus h, 1 plus h, and then 2 plus h. So I have -3, -2, -1, 0, and 1 as my x coordinates. Everybody okay with that idea? Okay. If I use the formula for my table, I'm going to have 3 times 2 to the -2 plus -4. I'm just going to write as -4 because plus and negative and subtraction are the same thing. So again, I have a times b to the -1 plus k. This is a plus k. A times b to the first plus k. And then we have a times b to the second plus k. So let's see, that's going to be minus 3.25. And that's going to be minus 2.5, minus 1, positive 2, and then positive 8. Again, you could use your calculator to simplify that if you wanted to. No big deal. Probably a lot of us aren't comfortable enough with the negative exponents to do those in our heads. Not a big deal. You just type it into your calculator if you need to. Next, I'm going to write down the equation for my horizontal asymptote. So remember, the horizontal asymptote can be found using y equals k. In this case, what is the value for k? -4. So my horizontal asymptote is just y equals -4. Pretty easy. So now I'm ready to draw my graph. See, so 1, 2, 3, and then 1, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. So the first thing I like to do is draw in my horizontal asymptote. So that's at y equals -4. So I'll just draw a horizontal line that goes through -4. And now I'm going to plot my points. So I have 3 and -3.25. I have -2 and -2.5. -1, -1. 0, 2, and then 2, 8. So there I've plotted my points. Now to draw my graph, remember you can't cross your asymptote. So the left end of my graph I'm going to draw like kind of parallel to my asymptote. And then I'll go through my points drawing a curved line. And I have arrows at both ends. And I'm going to be picky, again, about what your graphs look like. Specifically, the place I'm going to be picky about is the end of your graph that should be following the asymptote. So make sure you draw that end of your graph far enough out that I can tell that it's moving like kind of parallel to our asymptote. Places where I would be, things I would mark off for is if, say, you drew your graph and it looked like this, or you drew your graph where it looks like when you extend your line, it would cross the asymptote, right? Make sure you draw enough of your line so that I can tell that when you extend your arrow, it would not be crossing the asymptote. Do we get what I mean by that, Chloe?
Just really quickly, how do we know whether it's an arrow or a dot?
So for exponential functions, we're going to talk about domain and range right now, which is going to dictate like what the arrows are looking like. So let's go back and think about just our general form of our exponential function. Remember, the domain is all about the x coordinate, right? So I'm going to be looking at what values of x can I plug into a function that looks like this and still get an answer back, right? So we saw when we dealt with like square root functions, there were values of x that I couldn't pick because I can't square root a negative value. But when we dealt with like cube root functions, there was no restrictions on the x's I could pick because I can cube root any kind of number I want, right? So in this case, if that value of b is positive, are there any restrictions on that? No, I can pick any x I want, right? So what that tells me is when I'm drawing my graph for my exponential function, I'm always going to have arrows at both ends of my graph. And furthermore, it tells me the domain for my exponential function is going to always be positive infinity to negative infinity. There's no restriction on the x's I can pick. My domain will always be that. Does that feel okay, Chloe? I answered your question? Okay, good. Let's look at the graph we've drawn, though. Is the range going to be all real numbers also? It's not, right? So what's cutting off, or what kind of y coordinates am I going to be missing? all the stuff below the asymptote, right? The asymptote cuts our function off, so it can't go on the other side of it, so I'm going to miss all the y-coordinates that are on the other side of my asymptote, right? So in this case, those y-coordinates would be, or the range then would just be everything above the asymptote. So I'm going to have -4 to positive infinity. Notice here that I'm using a parenthesis on the -4 as opposed to the bracket. What was the difference between those two symbols?
The bracket was kind of a static.
The bracket meant that number was included in the set, and the parentheses meant it was not. Why are we not including -4? Because that's where the asymptote is, and the graph can't touch that. So I can't have a y-coordinate that corresponds to the asymptote, but I can have the first y-coordinate right after that, like -3.99999999999, you know, like whatever that first number is right after -4, which we can't write down because of the way the real numbers work and the decimal goes on forever. We have to write it that way. So in general, the domain is always this. The range, though, could be two situations depending on whether the A value is positive or negative. If the A value is positive, like we saw in our previous example, the range is going to be k to positive infinity. If the A value is negative, it's going to be negative infinity up to k. Because what the negative A value is going to do, it's going to reflect the graph. So now it's underneath the asymptote as opposed to above the asymptote. So that's all that's going to happen there. So easy to check that. All we need to do is look at the value for A, and we'll know exactly which situation we're in. Okay with that idea? Let's do one more graphing example, and then we'll be done. How's that sound? Okay, so let's say we want to graph y equals 3 times 1/2 x plus 1 minus 4. Well, I like to start by first writing down my values for A, B, H, and K. So what's my value for A? 3. And B? 1/2. And H? 1. And K? -4. Just as an aside, is this growth or decay? Decay. Again, because I can tell by the value for B. All right. Let's make our XY table then. So again, I use -2 plus H, -1 plus H, H, 1 plus H, and 2 plus H. And then to find the y-coordinates, I can either plug those x's back into my function, just use my calculator or whatever to get them, or I can use the formulas that I gave you. Either one is fine. So let's see what I do with that guy. 8, 2, -1, negative 2.5, and negative 3.25. Again, if you need to evaluate those using your calculator, just use your calculator, no big deal. I know probably most of us aren't comfortable enough dealing with like the mental math on the negative exponent to do that in your head. That's okay. Just type into your calculator exactly as it's written on your sheet of paper. Don't need to trouble yourself with that. Next up, let's write down our horizontal asymptote. In this case, it is y equals -4. Again, the k value is all we need to determine that equation for our asymptote. It's everything I need, so let's go ahead and draw our graph. That's not very straight. Neither is that. Okay, so I've made my xy axis. Next thing I like to do is draw in my asymptote. So again, a horizontal line that goes through -4. And usually I like to write down the equation next to it just so that it's clear to the reader what's going on there. And now I'm going to plot my points. So -3, 8, -2, 2, -1, -1, 0, -2.5, and then 1, -3.25. And I'll draw my graph. And I want to make sure that I draw enough of it that it's following the asymptote there, that it gets horizontal. Okay. And then the last thing here, what's the domain for this going to be? Negative infinity to positive infinity. The domain for exponential functions is always that. That's nice when we have an always situation, right? The range is, since the a value is positive, it's going to go from k to positive infinity. If the a value is negative, it would go from negative infinity to k. So that's the only one we have to worry about is the range, but it's not too bad. Everybody feel okay doing this? Shouldn't have been too bad today, right? So we'll stop here.